Welcome back to week 1, and in video 2 we are going to get into the details of the structure of the Earth's atmosphere. So what is it? What's the atmosphere made of? How is it split into different parts? Well, the atmosphere is a thin layer that's composed of various gases, water, and particulates that envelops the Earth. It extends to about 400 kilometers or more above the Earth's surface, and about 90% of its mass is in the bottom 10 kilometers due to gravity pulling all of those gases closer to the Earth's surface. And then the Earth's atmosphere actually consists of several layers or spheres that are based on various physical and chemical properties that we're going to discuss in the next few minutes here. So what gases are present? Your textbook has a great chart that includes the majority of the gases that are found in the Earth's atmosphere. I have the highest percentages listed here. So there's nitrogen, which is the highest percent. Some people think oxygen is the highest percentage in the Earth's atmosphere, but it is not. It's actually nitrogen. There is oxygen, which is composed of about 20%. Water vapor is another small percent. Carbon dioxide is another percentage, about 0.04, and then argon gas is about a little less than 1%. So those are the main gases present in the Earth's atmosphere. So one other thing to talk about is the hydrologic cycle and water vapor. So I mentioned back here in this previous slide that we have water vapor present in our atmosphere. And that water vapor gets there due to the hydrologic cycle. And this is where you have the hydrosphere and the atmosphere combining together and kind of working together to produce some important gases in our atmosphere. So hopefully this looks familiar from maybe previous science classes that you've had. So basically what we have a body of water on the Earth's surface, like a lake, a river, ocean. We have incoming solar radiation that heats up the Earth, or heats up that body of water, enough so that some of that water starts to evaporate, and so we get water changing from the liquid form to the gas form, and that's how we get that water vapor into the atmosphere. We can also get it through transpiration from trees. Once that water vapor gets in the atmosphere, it will travel from place to place. When it rises to a certain level, it starts to cool. That cooling, the air loses energy, so we then transmit or change the water vapor then into small little liquid particles in the atmosphere, and we get condensation in the form of clouds. When we have enough condensation occur and that those tiny little water droplets get big enough to the point where gravity is going to pull them out of the sky, we have precipitation. So snow, rain, sleet, hail, that kind of stuff. And then that water then returns to the Earth's surface through glaciers, rivers, surface runoff. It can infiltrate into the ground, get into groundwater, and then the cycle continues. So hopefully this is familiar, and we'll go through energy required for these phase changes from liquid to gas in our week 2 content. So one other question that comes to mind is, how does carbon dioxide and how do these particulates get into the atmosphere? Well, there's a few different ways. We have natural emissions of carbon dioxide from the decay of vegetation, volcanic eruptions, respiration of animals. And there's also man-made emissions of carbon dioxide from burning of fossil fuels and deforestation. Particulates that get into the atmosphere include volcanic ash from volcanic eruptions, dust when wind blows across the surface, dust can get kicked up into the atmosphere, salt along coastlines, we can get salt sprayed up and get into the atmosphere as well, and then smoke from fires. So those are just some of the main types. So here's just a diagram showing the carbon cycle, where that carbon comes from. So we have organic matter decaying to produce carbon dioxide. We have volcanoes erupting, emitting carbon dioxide and also ash into the atmosphere. And then we also have our man-made fossil fuel emissions also leading to increased carbon levels in our atmosphere. So getting back to the atmosphere, we're going to spend some time talking about the different layers of the atmosphere. So this is that envelope of gas, this kind of blanket surrounding the Earth. If we look at this side diagram here, we go from the Earth's surface, 0, and then we have kilometers on one side of the scale, miles on the other. And then these colored sections tell you the different layers of the Earth's atmosphere, so the troposphere, mesosphere, so on and so forth. And then kind of what features that hopefully are recognizable to you that exist in each. So basically at the surface, Earth's surface down here is the bottom of the troposphere. We go up to the next level of stratosphere, that's where weather balloons exist. Go up a little higher into the mesosphere, this is where when you see a meteor that's coming towards the Earth, that's where those exist. And then above that we have in the lower thermosphere, this is where we have the aurora that occur, and then towards the top is where the shuttle and the kind of orbiting satellites would be. So how do we divide the atmosphere into these different layers? There's 5 major methods. Mostly it's through thermal characteristics, so changing in temperature. We also have chemical composition, change from layer to layer, movement, and also density. So we're going to focus mostly on the thermal characteristics, and then your book can go into some of the others. So each of these layers, you'll notice they're bounded by what's called a pause. So for instance, at the top of the troposphere, we have the tropopause, and then at the top of the stratosphere, there's just stratopause. And that refers to where they have the greatest change in thermal, temperature, chemical, movement, and density. So that's where that major change happens. So I'm going to touch on this density. I mentioned in the previous video how density and pressure changes as you go from the surface of the Earth higher. And that is because you have gravity pulling those different gas molecules closer to the Earth's surface. So we have a higher density of air closer to the surface, all those gases, and then it decreases as you get further and further away. And then here you can see we've got elevation in green, and then we have millibars, or change in pressure, in yellow. And then we have where the planes fly, about 34,000 feet, and then the top of Mount Denali in Alaska, about 20,000 feet. So you can see we have higher pressure closer to the surface because we have more and more air weight above us. So how does temperature change throughout these different layers? So here, this graph will be familiar. You're going to see it on the next few slides. We're going to work from the bottom to the top in the next few slides. So basically the average temperature profile that you see here kind of varies. It zigzags back and forth, and where we have that biggest change happen is where you're going to have the division between each layer. So as we get higher and higher in our topmost layer, we have this kind of runaway heating that occurs. So in the troposphere, the bottommost layer closest to the Earth's surface, this is where we see weather. So where we see clouds, rain, things like that in the troposphere. And as we go from the surface of the Earth up, we see a decline in temperature. So on the bottom of this scale here, you see 0 degrees Celsius right about this location, and then positives towards the right, negatives to the left. And then we have miles on the right side, and then kilometers on the left. So the troposphere goes from about 0 to 12 miles, or 0 to 20 kilometers high. And excuse me, this is the layer in which we live. This is where we have all the weather being produced. The temperature drops as you get to the tropopause, and that transition between the troposphere and the stratosphere is called the tropopause, and that's where we see a drastic change in the trend of temperature. So as we move into that stratosphere, the temperature actually starts to increase as you get up towards the stratopause, which is the uppermost boundary of the stratosphere. And this stratosphere roughly goes from up to about 50 kilometers. These are kind of rough estimates. And the stratosphere holds about 19% of the atmosphere's gases. Very little water vapor, however. And we have a rough temperature change going from negative 60 to about 0 degrees Celsius roughly in that range. So this is where we actually have warm air on top of cold air. So what happens here is that warm air is kind of trapping that cold air, and it prevents convection from happening. So that's why when you see clouds, these huge cumulonimbus clouds that extend very, very high into the atmosphere, you see it kind of stop and flatten out at the very top. And that's because you're right at that boundary between those two layers. And then, of course, the boundary between the stratosphere and the mesosphere is called the stratopause. So into the mesosphere, we see a change. Again, we see the temperature start to decrease, just like it did in the troposphere. And it goes a decrease from roughly 0 to a negative 80 kind of degrees Celsius. And it kind of varies. You see that the temperature in my text is a little bit different. So it kind of depends on where you get your data from. And these are average values as well. So this can change and fluctuate as well. The mesosphere, this is where we have some gases that are still present here, and they're thick enough to slow meteors down. This is where we actually see meteors leave that trail. They burn up in the atmosphere in this layer, leaving those trails in the night sky. And then we get up to the mesopause. This is where we have our temperature actually start to change as we get to the mesopause into the thermosphere, and we see this runaway heating in the thermosphere. So this is the uppermost, one of the uppermost layers in the atmosphere. So we have increasingly thinner gases present in this layer, and this is where incoming high energy ultraviolet and X-ray radiation from the sun is actually absorbed by the molecules in this layer, and that's partially why we have this huge temperature increase. And that temperature increase can get as high as 3,600 degrees Fahrenheit. It's crazy. So this is what the astronauts have to get through when they're coming through re-entry into the Earth's atmosphere. So it's really, really hot. And then the last would be what's called the exosphere. Notice it's not on this diagram, it was on that first one. It's the outermost layer, and it extends from the top of the thermosphere to about 6,200 miles, about 10,000 kilometers. And this is where atoms and molecules actually escape into space, and this is where satellites orbit the Earth in the exosphere. There's one other way to divide up the Earth's atmosphere by looking at the ability to transmit electrically charged particles. This is called the ionosphere, and this is actually where, and the reason why we can listen to the radio and why radio waves can travel for such far distances. So this is because we have electrically charged gas particles that are present. It extends from about 37 to 190 miles, roughly 60 to 300 kilometers. These are also estimates. And it exists because there's radiation coming in from the sun and striking the atmosphere to create these charged particles. So these radio signals that are transmitted from the Earth are bounced back and forth from these charged particles, and that's why we can transmit radio waves across the world, basically. So as these radio signals are transmitted, some of the signal actually escapes to space. That's what you can see in the green arrow in this image down here. Some of the waves are transmitted through ground waves, which is the purple. And then this is what we actually hear. And then the rest of the waves, the red and blue arrows that you see, are called sky waves, and these bounce off the ionosphere and can bounce for thousands of miles, depending on what's happening up in the atmosphere. And then you see in your textbook, it can be divided up into different layers, which can vary with time of day because of the amount of incoming solar radiation. So that's kind of an overview of the structure of the Earth's atmosphere. Be familiar with those different layers. They'll become important as we move through the course. And we'll come back in the next video and talk about atmosphere and weather.